Chapter 12, Section 1 in the 8th grade textbook is entitled Graphing Linear Equations. So we're switching topics now entirely. We're going towards the end of the book now. We're going to switch into graphing. Graphing lines, graphing functions, graphing equations is a key concept of algebra. If you can have success with this here in 8th grade, chances are you'll have a great deal of success next year in 9th grade taking an algebra class. So here we're going to talk just about linear equations. The word linear, as you can see, contains the word line. So when we're talking about linear equations, what we're really talking about is graphing things that represent lines. And that's exactly what we start off with in terms of definitions, defining a linear equation. That's an equation whose solutions fall on a line on the coordinate plane. In other words, it makes a line. Again, a linear equation is an equation whose solutions fall on a line on the coordinate plane. Rate of change is a ratio that compares the amount of change in a dependent variable to the amount of change in an independent variable. What they're really talking about when that definition there, because I know there's some phrases in there we're not familiar with, is they're really talking about the slope of a line. Now, right now they're calling it rate of change, but very soon you're going to see that they're going to change that up and start calling it slope. Slope is simply how steep a line is, or I guess could be is not, depending on how the line is drawn. That's an amount that could be positive, it could be negative, but it's simply how steep a line is, and it's called slope. That's all slope is slope is a rate. Rate, remember, shows up like a fraction, a rate of change. It's a fraction that represents how much the line changes as we go from point to point. When they're talking about the dependent variable and the independent variables, that's where they're talking about our x's and y's, because we're talking about graphing on the coordinate plane. Your dependent variable represents your y's, your independent variables represent your x's. It is dependent because you have to pick an x, which is how it becomes independent, because you can pick anything, but then the value that pops out after we plug in x is dependent on that x value we picked. A certain x generates a certain y. So again, that's all they're really talking about there. When we boil down what they're talking about rate of change, all they're really talking about is the slope of a line. How steep a line is, or again, maybe if it doesn't look very steep, how steep a line isn't. And again, that value can be positive or negative. Again, a linear equation is an equation whose solutions fall on a line on the coordinate plane. Rate of change is a ratio that compares the amount of change in a dependent variable to the amount of change in an independent variable. All right, so let's go ahead and take a look at the first example here. In the first example, they're asking me to graph the equation and tell whether it is linear. So what we're graphing with here is what we call the table method. The table method is me generating a list of x values. Where did these come from? Well, I just picked some x values, that's all. You want to pick numbers that you're going to be able to easily graph. So you can pick 1,000 for x, but then you're going to have to go over there to the graphing piece and graph the number 1,000. That said, you probably don't want to pick 1,000 because you're going to have to make a big graph. But you're picking some x values, and then what you're going to do is plug them into this equation for x, where it is x is right here, figure out what y is, which is what this column represents. And then what you do is you combine the x and the y values over here, and that's your list of your coordinate pairs, because remember, the coordinate grid is a combination of x values and y values. So we picked 5 x's here. This would be a pretty standard list to pick 4 x's. The exception would be if I was multiplying perhaps by a fraction or a decimal, like if I was multiplying by 1/2 that was in the process. I probably wouldn't want to multiply that by 3 because that's going to still spit out a fraction. 3 times 1/2 would be 3/2. But if I picked multiples of 2, like 4, half of 4 goes to 2 and the fraction goes away. So unless it makes sense to do so, to pick other numbers, generally though you're going to see me pick the same list of 5 numbers over and over and over again. Okay, so we're going to plug each one in for x and figure out what this equals. So start with 0. 3 times 0 is 0, minus 1 is -1. 1. 3 times 1 is 3, minus 1 is 2. 2. 3 times 2 is 6, minus 1 is 5. 5. So, now, you notice I started at 0, went down this way, and I didn't go this way.
if it is a line, which here it is because we can see from graphing, if it is a line, there is always going to be a pattern that evolves here on this y list. So if you don't like working with negatives, or you're simply not good at negatives and you're sure it's linear, do what you can with the zeros and the positives and then figure out this pattern as it goes. As you can see, as we go up the list, what are they doing? Each time they're just subtracting 3. That prevents you then from needing to work with the negatives so much. But we go back here. 3 times -1 is -3 minus 1 is -4. 3 times -2 is -6 minus 1 is -7. All right, so now it's me all about combining the x's and the y's and then graphing those points on the coordinate grid. So the first one we've got there is -2, -7. Well, the x value of -2 means on the x-axis I'm going to go to -2, which is right here from the origin, 2 jumps to the left. Notice this grid box goes by 2, so when I say 2 to the left, it's just one whole jump. And then down to -7 and put a dot. Putting these two together gives me -1, -4, so I'm going to go left 1, which is just half of a jump. Again, it's going by 2s. And then down to -4, which is marked. Put my dot. 0, -1 means I don't have to go right or left because the first number is 0, but to get down to -1, I'm going to have to go down half a jump. Again, since this is going by 2s, a half a jump would be 1. 1, 2 for the next one means from the origin I'm going to go right 1, up 2, put my dot. Again, half a jump and 1 jump since we're going by 2s. And then 2, 5 means from the origin I'm going to go right to 2 and up to 5, right a whole jump and up 2.5 jumps. Again, since it's going by 2s, connect my dots. And as you can see, what do we have graphed here? We have graphed a line. Because we've graphed a line, that's what's going to make this be linear. All right, that's what they're explaining in the paragraph at the bottom. Because we've graphed a line, it is linear. Now, another way we can figure out what they're doing there in that graph without necessarily sketching out a coordinate grid each time is to look at the table of x and y values. So here, they're asking me to determine whether the rates of change are constant or variable. So what they're talking about here is, here's your table of x and y values. Now notice what they didn't give us here is they didn't give us the equation. So can't just look at the equation and figure it out that way, but we can certainly go from the table that they've given us and figure it out going that way. So taking a look at what they're doing here is they're going to figure out the distances in each jump for the x's and the y's. So look here, to go from 0 to 1 on this first x jump would be a distance of 1, which is why they wrote 1 here. To go from 1 to 3, that would be a distance of 2, which is where 2 came from. To go from 3 to 5 is a distance of 2, which is where this 2 came from. And to go from 5 to 8 is a distance of 3, which is where that came from. Now we're going to do the same thing on the y column representing the same jumps. To go from 0 to 2 is a distance of 2. That's where this answer came from. To go from 2 to 6 is a distance of 4. That's where this answer came from. To go from 6 to 10 is a distance of 4. That's where this answer came from. And to go from 10 to 16 is a distance of 6. That's where this answer came from. Now what you're going to do is calculate the rates of change that represents each of these jumps. What they mean is to write these guys as fractions that represent the changes here. Now, one thing you'll see down here that we talked a little bit about in the introduction with the definitions is they wrote these like they would write slopes. Again, that's that rate of change definition there. Slopes always compare the change in y, or the change in y values, with the change in the x values. So even though it doesn't really have any significance right now in this particular isolated problem, we're going to do it that way so when we get there, we're not confused. So they're going to write each of these jumps in the same distances as fractions. So here the first jump, 2 for the y's, 1 for the x's, 2 over 1. Second jumps, 4 for the y's, 2's for the x's. Again, we're talking about the changes. Third jump, 4 changes for the y's, 2 changes for the x. 4 over 2. Last jumps. 6 is the distance and the changes in the y's. 3 is the changes in the x. 6 over 3. Well, notice when we reduce each of these fractions, they all reduce to the exact same thing, 2. Because they represent all a change of 2, that means that the rate of change is constant. Constant meaning the answer is the same each time. Variable would mean somehow at some point at least one of them is different, or maybe they're all different. But these are all 2, so they're all the same. That means there's a constant rate of change. When you have a constant rate of change, what you have is a linear function or a linear equation. So looking at this table without making a graph, you can sketch one if you want to, but I can tell you that this represents a linear equation, or this is linear, which is exactly what we could have then done back on that previous example. Without making the graph to figure out if it's linear or not, we just look at the data table there. We see the changes, and we see the changes when I compare the x's and the y's is the same each time. And since the amount of change is the same each time, that means that that's going to be a linear function. If just at one point here we would have popped out an answer 3 with everything else being 2's, all of a sudden the answer becomes variable. All of a sudden this isn't a linear function, it's something else. And that's all. Okay, so let's go ahead and continue on here now that we've seen a couple different ways to figure out if things are linear or not. And let's go ahead and take a look at question 3. It says, lift on a ski slope rises according to the equation A equals 130t plus 6250, where A is the altitude in feet and t is the number of minutes that a skier has been on the lift. 5 friends are on the lift. What is the altitude of each person if they've been on the ski lift for the times listed in the table? Draw a graph that represents the relationship between the time and the lift and the altitude. So, as you can see, what they've done here is they've taken this equation and they're plugging in some different times here to figure out where these people are. Now, realize here, where did these come from? Yes, this is just like x earlier. You can pick whatever numbers you want. But then there's this little table over here on the right side that's going to help us compare the time. Well, notice here the biggest time, which is what t represents in this equation, is 4. And it goes on down to 1, which is why they've picked these particular numbers. Yes, I can pick any time I want, but they're not relevant all to this equation. These are the times that are relevant. So they've picked all of these times here to plug in for t, and then they're going to solve the equation. Now, if we were talking about graphing, and this was really bothering you, we can fix it. Because, of course, if we're graphing, we'd be graphing x's and y's, which is what we're going to do in a minute, because that last line says to draw a graph. All right, so if it's bothering you that there's t's and there's a's here, when there should be x's and y's, because that's how we've learned to graph. Now that we've got set up, let's do it. Change it to x's and y's. It's not going to hurt anything. So change this to x's just like we learned earlier. Got to change it up here in the equation too. And change this to y's. Just do the same thing up here in the equation. Now it says y and x. Now it looks like something we'd be comfortable graphing because we have x's, we have y's. Our coordinate grid is x's and y's. No big deal. All right, so let's plug each one of those numbers now into the equation and see what happens. When I change x now into 4, I'm going to do 130 times 4 plus 6250, which is good because that's perfect order of operations. The result is 6770. At 3, 130 times 3 plus 6250 is 6640. At 2, 130 times 2 plus 6250 is 6510. At 1.5, 130 times 1.5 plus 6250 is 6445. And here for the last one at 1, 130 times 1 plus 6250 is 6380. Now remember, A, which is now y, is the altitude in feet. So in other words, how high up these people are. So this column here, y, represents how high up these people are. All right, these numbers over here represented t originally, All right, now we're calling it X because we're going to graph it. All right, that is how long they've been on the lift. So the longer we're on the lift, the higher up we are. That makes sense. That's the relationship here that we're going to end up talking about here when we go to graph. The higher up we are, the longer we've been on the lift. Makes sense. All right, so let's continue on. We've filled out the table there. Now we're going to go ahead and go down and take a look at the graphing here. All right, so Anna's at 67.70, Tracy's at 66.40, Kwani's at 65.10, Tony's at 64.45, and George is at 63.80. So we're going to go ahead and graph those here. All right, the person that was 1 minute into the ride is at 6,380 feet. That was George. The person 1.5 minutes into the ride, that was Tony. He was at 64.45. So I went over to 1.5 and up to 64.45 and put a dot. 2 minutes into the ride was Kwani. He was at 65.10. So I'm going to go over to 2 and go up to 65.10, put my dot. 3 minutes into the ride, well, that's where Tracy is. She's at 66.40. So I'm going to go over to 3, up to 66.40 and put my dot. Finally, 4 minutes into the ride, we'll find Anna. She's at 67,070 feet. So I'm going to go over to 4 and up to 6770, put a dot. Notice what we have here. We have a line, all right? Because we've graphed a line, that makes us a linear equation. Let's put that together with what we saw earlier, though. We can tabulate the changes here and make sure that the changes represent the same distance here. Well, as you can see, they actually already did that for us here. Every time we go up by 1 unit, from 1 to 2, and 2 to 3, and 3 to 4. Now we can do this half one. I'm not skipping that for any reason other than the fraction would reduce to the same thing. So you can do it if you want to figure it into the half, but every time we jump over 1 full unit, all right, this altitude is going up by 130. Well, because that amount is changing at the same pace for every marker here from 1 to 2, 2 to 3, and 3 to 4, that means that that rate is constant like we saw earlier when we manipulated the table. And because that rate of change is constant, every minute it's going up 130 feet, all right, that means that this is also a line based on the slopes being the same. Again, you can prove that either way, but the fact that it is a line when we graphed it or the rate of change being constant would also imply that this is a line. All right, so let's go ahead and take a look at the concluding examples here. Number 1 is asking me to graph the equation and tell whether it's linear, and the equation is y equals 2x plus 1. Again, linear, all that means is when we graph it, it's the graph of a line. Okay, so again, what we're going to do here is we're going to go ahead and pick some x values here and graph them. I'm going to go ahead and pick that same list I picked earlier, -2, -1, 0, 1, and 2. I'm going to plug each one of those in for x and figure out what the corresponding y's are. I'm going to start with 0 like I did earlier. 2 times 0 is 0, plus 1 is 1. At 1, 2 times 1 is 2, plus 1 is 3. At 2, 2 times 2 is 4, plus 1 is 5. Now, it certainly looks like as we go up the list there's a pattern here. It looks like we're knocking 2 off each time. So let's see if that works, because if it works, we know it's going to be a line because the rate of change is going to be the same each time for the reasons we talked about when we saw that table question earlier. It doesn't necessarily have to be, but then it's not going to be linear. Since we've already seen the graph, we know it is linear, so it is going to work, but let's check it out. At -1, 2 times -1 is -2, plus 1 is going to give me -1. And indeed, as we go up here, they are subtracting 2, so I don't have to figure this last one out. It's -3. We're going to come over here and sketch ourselves a little graph here. -2, -3, left 2, down 3, put a dot. That's this guy right here. -1, -1, left 1, down 1, put a dot. Notice that's right on top of my line as well. 0, 1, which is this point right here. 1, 3, I'm going to go right 1, up 3, put a dot. That's also right on top of my line, even though they didn't plot that. And 2, 5, right to up 5, put a dot. Again, if you're struggling with the graphing, the first number, the x number, always represents something on the horizontal axis. The y value always represents something on the vertical axis, the one that goes up, down. So figure out where it is on the x, then figure out where it is on the y, match them together, and that's how you graph your points. We've been graphing points for a long time now, not in the terms of graphing a linear equation, but just graphing regular points. That's something you should have familiarity with. Connect the points. Obviously, we've graphed the line, so it has to be linear. Final question there is asking me to determine whether the rates of change are constant or variable. So let's go ahead and calculate out our changes here. To go from 0 to 1 is a change of 1. From 1 to 2 is a change of 1. From 2 to 3 is a change of 1. From 3 to 4 is a change of 1. That was easy. Taking a look at the y numbers, to go from 1 to 3 is a change of 2. 3 to 5 is a change of 2. 5 to 7 is a change of 2. 7 to 11 is a change of 4. So as we go through and calculate the changes, first change is 2 over 1. Again, we're always going to do this y change first because slope represents a change in y over change in x. Again, it doesn't really matter in this section. It's not going to impact your answer if you don't. But very soon, you're going to have to write it as y over x when we talk about slope. So let's just get in good habits here. 2 over 1 for the first jumps, 2. Second jumps, 2 over 1, 2. Third jumps, 2 over 1, 2. Last jump, 4 over 1, 4. All of a sudden, the number is different here. That means the rates of change are variable. That means this isn't going to be the graph of a line. This is not a linear function.